Hello everyone, welcome to another lecture for drug delivery engineering and principles. Let's do a quick recap of what we did in the last class. So we are continuing our discussions on hydrogels. As we already discussed, what are hydrogels? Hydrogels are these highly hydrophilic kind of gels that are made from hydrophilic polymers, and they have the capability to absorb lots and lots of water, and they can swell. So why they are very important is because first of all they are very similar to how the tissue normally is. So if you look at the tissue, lots of ECM components are sort of hydrogels themselves. They are extremely hydrophilic, and they are sort of encapsulating all kinds of cells, where cells then use various processes to synthesize more ECM as well as do their normal functioning. So within the hydrogels we had discussed quite a lot of variations of them. We had discussed physical, we had discussed chemical, and then we also discussed ionic hydrogels. And then we further went ahead in the last class and we talked about in situ cross linking gels. And so what are these in situ cross linking gels? That means that they cross link at the site, and the interest of the site for our application is the human body or any body. So in that sense that means that when we inject these hydrogel precursors, which are typically in liquid formulations, into the body, they will cross link right then and there, and this could be on the basis of several things. This could be on the basis of time, this could be on the basis of temperature. So all of these are fairly feasible. And then we discussed a paper in which maleimide was used as one of the cross linking method for making hydrogels. These are PEG based hydrogels that we talked about, and maleimide was one of the chemical group that was reacting with thiols. So this was PEG with reacting with peptides that had thiol on both ends, and this PEG was of course the 4-arm PEG with maleimide at the 4 ends, and that essentially led to the cross linking. And what we found was basically there were several chemistries that can lead to the production of the hydrogels, but among the 4-5 moieties that this group had compared, they found that maleimide was by far the most efficient as well as well suited for any in situ applications as well, because the gel was then able to cross link and then adhere to the tissue as well. Okay, so now that we have described all this, we are going to discuss some of the maths today as to how we can compute what is the pore size, what is the different formulations that leads to different pore sizes. So how do we go about doing that? So for the purpose of this class, we are only going to talk about neutral hydrogels, and we are going to define few of the terms and few of the equations as we go along in today. So the first thing is the Flory-Rehner theory. And what it is, it is basically a theory that defines how the cross linking of the polymer gels happen. So what they are proposing is there is a Gaussian distribution of the polymer chains that is found in nature, and that is a good assumption to make given what we see in the literature. And the degree to which a polymer network will swell is going to be governed by the elastic retractive forces of the polymer chain as well as the thermodynamic capability of the polymer. And so what essentially this means is, let us say I have a polymer that is cross linked. So now as I said, these are hydrogels and they tend to absorb water, but there is some limitations to it. Of course thermodynamically it is favorable for the water to go in and interact with these polymeric chains. So that is where the thermodynamic compatibility of the polymer comes from, whereas as it continues to absorb water, these chains here will get stretched. So eventually this is going to get to a formation like this, and let us say if they continue to stretch, they are going to get to a formation like this, but eventually these chains themselves will start to have tensions, because obviously they are sort of cross linked at these sites, and there is a limitation to the amount that these can be stretched. So that is where the elastic retractive forces come in. So now these chains are going to try to bring this polymer gel back to its original state, and so it is sort of the force balance between these two forces, the affinity for the water to get absorbed into the system as well as the elastic retractive forces of these chains to sort of resist that and go back to their original state. So, essentially that is what will define is at what stage at equilibrium the hydrogel will stop, right. So, now that we have that concept clear, so therefore, the total free energy upon swelling will be given by what will essentially be the total free energy will be equal to the free energy because of the elastic forces as well as the free energy because of the mixing. Now, with respect to the number of solvent molecules in the system, we are saying at a constant temperature and pressure. Of course, if you change this, the final state of the hydrogel will change. If you increase the temperature, maybe it will swell more. If you change the pressure, maybe it will swell more or less depending on what you are doing with the pressure. So, we can then essentially convert this delta G to delta mu, which is the chemical potential change, and we can basically say that whatever change we are seeing in the chemical potential will essentially be equal to the change in potential due to elastic as well as the change in potential due to mixing, and the mixing is of course the thermodynamic mixing of the water with the polymer chains. So, again as I said, the mu 1 is the chemical potential of the solvent in the polymer gel as well as mu 1 0 is the chemical potential in the pure solvent. So, we are assuming that it was formed in some pure solvent and then it is mixed into sort of this new solvent now in the polymer gel now. So, but we know at equilibrium it will not really change its state. So, basically it would have attained already this balance between these two forces. So, we know that at equilibrium the left hand term, which is the change in the potential, will become 0. So, that means that then the elastic and the mixing chemical potential change will have to be equal to, so that they balance each other out. Okay. So, now that we have established that, let us see how we can define the delta mu for mixing. So, this is of course related to the heat of mixing and the entropy of mixing. So, this can be defined directly as delta mu mixing is equal to the RT with this expression, where, and I am not going to go into the derivation of all of these equations. So, where we know that the chi is the polymer solvent interaction. So, how the polymer and solvent are interacting. So, this is going to change if you change the polymer, this is going to change if you change the solvent. And then V2, as we have already defined before, is nothing but the polymer volume fraction of the gel. What about the elastic chemical potential change? So, for cross-linked gel in absence of any solvent is calculated by the rubber elasticity theory. So, of course, this case when we are saying in the absence of any solvent is sort of non-existent, because the hydrogel will only form when there is some sort of solvent. You can't expect just the polymer chains to just mix, because there will be no diffusion, no sort of interactions happening. So, this is just an hypothetical case for now, but the delta mu elastic for these gels will essentially be calculated by the rubber elasticity theory, and this can be expressed as delta mu elastic is then expressed as this term, where again now we have defined couple of terms. So, this is the specific volume of the polymer. So, essentially what is the specific volume of the polymer itself? V1 is the molar volume of the solvent. So, it then defines as to how much of the solvent is there. Mn is the molecular weight of the linear polymer chain. So, this is essentially how big your chain is. So, of course, that is going to help with that. And what is Mc? Mc we have defined before is the distance between the cross link. Okay. So, essentially as we discussed in the last slide, they have to balance out each other. Since these two terms should balance at equilibrium, we can then equate and sort of solve for what is the MC with other terms, and again MC was the length between the cross links, the average length between the cross links. Okay. So, now that we have this mathematical term, as we already said in the previous slide, that this is in the absence of any solvent, and this is not really any physiologically relevant. This all the cross linking in the hydrogel you will see is going to be in presence of some solvent. So, now if I add the solvent and try to correct this equation to reflect that, what I will do is this was done by modification to the Flory-Rehner theory by Peppers and Merrill, and what it is done is we have to include the volume fraction density of the polymer chains during cross linking. So, we have defined a new term called V2R, which is essentially the volume fraction of the polymer in the relaxed state. And when I say relaxed state, what is relaxed state? So, let us say if I am doing the synthesis of the hydrogel in let us say 100 microliter of a solution volume, and the hydrogel is formed, then as when it is immediately formed, what is the sort of the volume polymer fraction at that state. So, this is relaxed state, which essentially is just formed. Obviously, as more and more time is given, this, because it wants to interact more with the water, will essentially starts to swell, and at some equilibrium it will stop. So, we can call this one as swollen state, right. Or alternatively what we can do is we can let it dry off, we can use some high vacuum, or we can just dry it in the air, and so this is dry over time, this was time in water. So, if I let it dry off, these polymer chains will further collapse, and this is essentially nothing but dry state. So, we have just defined relaxed state, swollen state and dry state. Obviously, in dry state if we are saying that we completely dry it off, that there is no water present, what will that give you? That will essentially give you what amount of weight did you actually started with. So, so these are the couple of terms. So, but basically that previous equation for mu elastic then gets corrected by this term of V2R, so which is then reflected here. Okay. Now that we have done that, so again relaxed state is basically immediately after cross linking, but before swelling. So, then we can now equate the delta mu mixing with delta mu elastic like we did in the last slide, just because it has to be balancing each other out at equilibrium state. And then what we get is essentially a modified equation which then defines MC as a function of several other parameters that we can sort of compute or determine using various techniques. Okay. So, continuing further with the rubber elasticity theory. So, hydrogels, these are again similar to natural rubbers. So, the ability to deform is readily basically under low stresses can be changed. So, they can be considered to be elastic essentially. So, right now we are talking about how this rubber elasticity came up. So, we are saying that for deformations which are less than 20%, we can say that these are elastic deformations, and this was originally developed by Trioler and Flory for rubber, and then was later modified by the Flory to reflect it for hydrogels. And again, as I said, that theory was developed initially to reflect the change in absence of solvents, and then it was further modified by Peppers and Merrill. And with the rubber elasticity theory, they are saying that tau, if tau is the stress applied to the polymer sample and rho is the density of the polymer itself, then you can sort of equate them on the basis of this equation. So, now we have another equation. So, tau is something that we are applying the stress for. So, we can use some instruments like rheometer and all to know what is the tau, and that will give us another equation along with the last equation to be able to sort of get some sort of an idea as to what are the different MC and V2S and V2R. And then again alpha here represents the elongation term. So, this is basically the elongation due to the applied stress, and as I said, a tensile testing apparatus can be used to sort of measure these rubber elasticity for hydrogel samples. Okay, so let us if we now have to do what is the pore size calculation, which is what eventually we want to get at. So again, this is the one of the most important parameters in controlling rate of drug release from a hydrogel, right, because if I have for the same drug and for the same concentration, if I change the pore size from let us say 10 nanometer to 15 nanometer, now it will be much easier for drug to sort of diffuse out from the hydrogel network than it will be when the pore size is low. And so that is one of the most important parameters that we have to define. I can't really try to deliver let us say a drug which is 50 nanometer in diameter through a hydrogel that only has pores of 10 nanometer, because those drug molecules will not be able to even physically come out from the hydrogel. So this is something that we definitely need to define, and then we can again we can directly measure that using some techniques like electron microscopy or light scattering. The problem with the electron microscopy is this is typically done in high vacuum. So even though you will get sort of some idea as to what is the pore size, but then since this is done in high vacuums, is essentially giving you a pore size in dry state. However, when we put this hydrogel in our body or use it for any biological applications, it is always going to be in aqueous media, and now since it is in aqueous media, this pore size will change because it has much more water around it, there is going to be swelling and all that, and so the value you will get is not going to be accurate. So you can't really trust this high vacuum data for the pore size, even though you can then use this to compare between different hydrogels, but that comparison will also have some caveats to it. So as we said, the molecular weight between crosslinks is sort of an indirect measure to the pore size, right. I mean, if I am saying that if this length is MC, as this length increases, the pore size will also increase. So it is some sort of a measure for that. So the mathematical expression of the pore size is then given by nothing but the elongation of the chain itself as well as multiplied by the R0 square under root. So basically the root mean square of that, which is the unperturbed end to end distance between the polymer chains. So essentially this is MC itself, but defined in some other way so that it is always positive. So now assuming that and assuming that there is isotropic swelling of the gel, so that means that so what that means is, let us say if this is the swelling, then it is having isotropically, which means that all these lengths will increase rather than just having an increase like this. I am saying that this is wrong, but this is correct, this is isotropic swelling, and that is a good assumption to make unless there is some inhomogeneity in the gel. So if I assume that, then what we can say is that the alpha, which is the elongation, is nothing but is going to be proportional to the cube root, the negative cube root of the V2S, which is the volume fraction in the solvent, and then the R0 is calculated through the Flory characteristic ratio n, which is then defined empirically like this, where L is the bond length along the backbone. So typically 1 to 1.5 to 1.7 Armstrong for different polymers. Here is an example of 1.4 Armstrong for vinyl polymers, and n is the number of links per chain. So if I know what is the bond length, I am saying there are n number of links per chain, which is related to the cross linking density as well. So m0 being the molecular weight of the polymer of the monomer will come, this will turn into n is equal to 2 mc divided by m0, right. So essentially we are saying if this is the chain and the between the backbone, each bond is, let us say 1.54 Armstrong, this is for the vinyl polymers, and is the number of links per chain. So how many links of such are there, then we can sort of define n as the 2 mc by m0, where m0 is basically the total molecular weight of the chain, right. So if I combine these two equations, the pore size of the solid network can then be expressed as nothing. So all I am doing is like combining the previous equations with these equations, and what I will get is a value for the pore size defined with some other terms, and that is how I can then find what is the pore size of my hydrogel. So, quite a complex calculation up to here, but then I will give you an example now of what is typically done in the field if you are making a hydrogel, which will make it simpler. So, here is a specific example. So, this is a specific example is looking at polymerization of two different types of PEG. So, you have an oligo PEG fumarate and a PEG diacrylate. It is again a radical reaction, you use some sort of initiator. So, in this case ammonium persulfate, and what will happen is these radical bonds will start to react with the PEG fumarate, essentially leading to a cross link network, which is defined here, right. So, if I am saying so this is of course example from Miko's group at Rice University in US, and what they have done is they have formed hydrogels which they have called OPF hydrogels, and the PEG diacrylates can be used by a radical initiator like ammonium persulfate to sort of without the need of UV light, and then there are ester bonds that are formed which are again hydrolyzable. So, all of these ester bonds, these can be degraded by water, and the original purpose of this hydrogel is to kind of use it as a tissue mimic, sort of use as a control release potential, as engineering matrices and all. So, let us see what they have done in terms of characterizing what is the pore size of this particular hydrogel that they have formed. So, what they did is they for the PEG they have different molecular weights PEG that they have used. So, they have formed 3 different types of gels defined as PF10K, PF4K, PF1K, and that is essentially telling you what is the length of the PEG that they have used. And then what they did is just to form the gel they use these cell culture plates which typically have wells, and depending on how big that cell culture plate is, these wells can be 10 millimeter, 16 millimeter, or something else. So, in this case they have used 10 and 16 millimeter discs, and then once they have formed it, so that is the relaxed state, and then what they have done is then they have taken these discs, because now the hydrogel acquires whatever shape was there and this is a disc shape. So, they have now taken these discs and placed it into a very large volume relatively compared to the gel size of water at 25 degree Celsius. And then what they did is over time they have done, so at the time the disc were formed at time 0 they have weighed that, and then they have continued to weigh it at different times, right, and then they have also measured the diameter, which is basically using calibers already defined here as 10 millimeter or 16 millimeter. So, now how do you calculate the swelling gel, the swelling ratio? So, you are saying that if it has swelled, it is because lots and lots of water has went in. So, we are saying that because the water has went in, after swelling there is a certain weight Ws, and before swelling there is a certain weight Wd, and then the ratio is basically how much it has swelled. If it swelled twice, then what has happened is now we have a swelling ratio of 1. So, it has become double the size. And so, now they have determined, and what they found is if they are using a 1K, 4K or 10K, they find that the swelling ratio is different. Notice how if as you are increasing the molecular weight of the chain, the swelling ratio is dramatically increasing, right. It has become all the way up to 3 as you have increased the molecular weight of the chain that you are using. So, now they can apply the Pepper's-Merrill equation for MC, and again just reiterating it here, here is the tau, right. So, now if they want to apply that, there are several parameters that they do not know. What is V2S, what is V2R? So, these are easy to find out. So, what they can do is they can use the hanging pan and kind of measure this. So, V2R is nothing but weight of the polymer divided by the weight of this term, and then similarly Vp, which is the volume of the polymer, is nothing but how much you have added the water divided by the density. So, once you apply all these equations and get some of the values from different parameters reported in the literature, you can do this in different solvents as well. You can do this in hexane, and so what you end up with is essentially applying and fitting all these values, you get a MC for different gels. So, you have PF1K, PF4K, PF10K, and notice how the molecular weight between cross link has also increased. So, it has went all the way from 2000 grams per mole to 6250 grams per mole. And then once you have that, you can just directly put this into the pore size calculation and essentially just apply this throughout, where we have 1.47 is the Armstrong length between these polymer bonds in the backbone. So, if you apply that, what you will find, and Cn is basically taken from the literature, and what you will find is the pore sizes increases from 76 Armstrong, which is essentially 7.6 nanometer to 16 nanometer. So, this sort of reiterates that if you increase the molecular weight of the polymer itself, you will get a higher pore size. Okay, so we will stop here. These are some of the terms that we have sort of used to define what is the pore size, what is the molecular weight between cross link. Lots of complex equations here. We have assumed some of the things here, as well as we have taken these equations from the literature and not went into the derivation. So, this is just some of the ways that you can determine what is the pore size of a hydrogel that you are making or using. Okay, we will continue in the next class.